Hey everyone, and welcome to part 7. So in this part, our primary goal is proving something called Lindenbaum's theorem. And Lindenbaum's theorem says any consistent set of axioms delta can be extended into a maximally consistent set, a maximally consistent theory, gamma. And I never really defined extending something, but it's almost not even worth a definition, right? Sigma is an extension of delta. Get ready for this, if delta is a subset of sigma. So an extension is just these are all sets of sentences. An extension is just adding more sentences, right? And of course, a consistent extension is just an extension that is consistent, right? Okay. All right. So that's the statement here. And we're going to get into the proof immediately. But before I do that, I just want to say one thing, which is for most of this, I'm going through a textbook and presenting in very much the results in the order, and I'm going off of that. But for this in particular, the proof is kind of unwieldy, and so I'm presenting an alternative proof that I think it's simple enough, and it's so obviously equivalent to their argument that I feel it's very obviously equivalent to their argument, and it's so simple that I'm sure that this is like I think this is something. This is a different way to prove it that surely has been written in some textbook somewhere, but not the one that I'm using. So I could be wrong on this because I'm presenting a proof of my own creation, but it's very much so, very much so similar to the one written in this book. So I'm just saying that so that I apologize if there's a mistake in it. This definitely doesn't have the same level of scrutiny as the other stuff I've been presenting, which has been based off of what I've been reading in this book. Okay, so yeah, so let's just with that prelude out of the way, let's dive into the proof. Okay, so I probably won't need to refer to this name, but we'll let F be the family of consistent extensions of delta. And if you recall from Zorn's lemma last time, Zorn's lemma lets us conclude the existence of a maximal element of a family, provided that we've demonstrated some condition. So Zorn's lemma, with this construction, Zorn's lemma would make this immediately, right? It would give us the result immediately, applying Zorn's lemma here, because if we have a family of consistent extensions of delta, then a maximal element in that family is a maximal consistent extension, which is what we want to show the existence of. So we're going to go right towards Zorn's lemma, and what we're going to do, we wish to show every chain C is upper bounded. So in this situation, what does a chain look like? Let's try to do a brief example to understand that. So a chain might be, for instance, of course, delta is the smallest element that is a consistent extension of delta. So maybe delta is the first element of the chain. And then maybe the next element is delta union the statement P. and then it's delta union the statement P union the statement P and P. And then maybe it's delta union the statement P union the statement P and P union the statement P and P and P. Okay, so I'm picking this example because this is obviously consistent, right? Each of these is no stronger of a statement. Each statement is no stronger of a statement than what's been previously added. So this is definitely a consistent chain. But this is an infinite set, right? This is an infinite this is an infinite collection. So the difficulty is and this is what makes Zorn's lemma a necessity, and it's also what makes this difficult, is that we need to show that there's some consistent extension, right? So I'm only adding finitely many sentences at any time here, but we need to show that there's a consistent extension that it's necessarily a infinite consistent extension, and that it's still consistent, and that it contains all of these infinitely many statements that I'm appending to delta, right? So that's the difficulty. Okay, so hopefully that's an example. This is our first example of seeing an infinite chain, so I thought it was worth showing that. So it's really the infinite chains that are interesting. Of course, the finite chains are much easier, but the infinite chains are interesting, right? So we'll pause for a moment here. So we have a chain C, which is some sequence of extensions of delta. What does an upper bound of C look like? Or what do you think the upper bound of C is? Think about that for a moment. Okay. So immediately, it's actually just the obvious one. So we'll let sigma be equal to the union across everything in the chain. So if the chain is I take, you think of it as the limit of the chain or whatever, but if I have P and then I take P and P and then I take P and P and P, the sigma would be all of the statements. It would be adding in all of the statements that are just conjunctions of P, right? And it's not adding in one infinite statement. It's adding infinitely many finite statements in. Okay. Okay, so clearly, we don't even need to prove this, right? But clearly, for all C in C, C is a subset of sigma, right? Just because this is a union, so that's obvious. So it's clear that certainly that sigma, it's clear that certainly sigma is an upper bound, except the one remaining thing is sigma is definitely an upper bound, but is it in this, right? So basically, it remains to show, and maybe now, I like to pause a lot because it's helpful to try to follow the reasoning. What do we need to show? What's left? Think about that. Okay, so it remains to show that sigma is consistent, right? So we've shown that that sigma is certainly an upper bound on the chain. But in order for it to be an interesting upper bound, of course, I could have just taken every sentence and called that the upper bound to everything, right? So it's important to show that sigma is consistent so that we know that we're still working within the family of consistent extensions of delta. So the actual challenge is proving that this infinite set is consistent. That's actually the meat of the proof. And so how do we do that? This is a little harder. And we'll be doing this with a... We'll be doing this with a proof of contradiction. So suppose, and I won't ask you to think through these, so sigma is not consistent. So what does that mean? Well, from last time, that actually means, this means, so of course, there's a lot of things that sigma means, but what this means for our purposes is that sigma proves some contradicting, sigma can prove some obviously false statement, right? That's what it means to be not consistent. Or we've shown last time that it's equivalent to being not consistent, okay? But this means there is some finite proof, and I'll call it psi1, psi2, psi n, and this is a finite proof of P and not P. Okay. So if our upper bound, I'm just going back through it one more time. So if our upper bound here is inconsistent, that means it has to prove a contradiction. And since it has to prove a contradiction, there must be a finite. All proofs are finite, so there must be a proof of the contradiction, and of course that proof will be finite. So let, or where's my color? Okay, so let, and now we'll let, I guess I'll call it sigma prime, subset of sigma, be only the statements used in the proof. Okay? So sigma prime is only the statements used in the proof. And importantly, this sigma prime is finite. Okay, so the idea is if sigma is not consistent, then it can prove a contradiction, which means it can prove a contradiction. Every proof is finite, so it can only rely on finitely many things, right? So I can take the finite set of everything I actually used in the proof of sigma, or I actually used in the proof of the contradiction, right? And now, kind of the big reveal is now sigma prime is actually a subset of S for some S in the chain. Okay, so why is that true? Well, why is that true? Well, the important thing is that there's only finitely many, right? So every statement in, I'm not going to write this out because this is somewhat obvious, but I will explain it, right? So every statement in every statement in sigma, because if we go back up here, sigma is the union of everything in this chain. So every statement in sigma occurs somewhere in the chain, right? At some point in the chain, it occurs. So if I have a finite collection, I can just look and figure out where in the chain each sentence occurs, right? You know, so the first sentence, you know, if this is the set, you know, phi 1, phi 2, and phi 3, I just need to find C1, or I'll write this down here and then erase it. So if sigma prime is phi 1, phi 2, and phi 3, then I just need to find C1 where phi 1 occurs, C2 where phi 2 occurs, and then C3 where phi 3 occurs, and then just take the largest one. And then that will contain all the other ones, and thus it will contain all of sigma prime, right? So, but this is, right, okay, so hopefully that makes sense. But this is a clear contradiction, since everything, or since C, let me just scroll down even further, was assumed to be consistent. Right, so the point is the chain is only consistent sets. So I've constructed, if the upper bound isn't consistent, I can construct some element in the chain that must be inconsistent. And that means that I can construct some element in the chain that must be inconsistent. And that contradicts the fact that everything in the chain is consistent. Ooh, I did not even start very... All right, so we're zooming out a little bit in the paint. And we're pushing back up here to give myself a little bit more space in doing this. Because I definitely need to keep all this on the screen at one time so that so that I can keep scrolling back up and referring to things. Okay, so before we move forward, I've actually proven a lemma that is far more useful. I've proven a lemma that's far more useful than just this proof. So let's actually discuss that right now. It's almost, or how to phrase this actually. Actually, no, I'm not gonna state this yet because there's a very equivalent model theoretic statement that we'll get to immediately. But this is our first instance of something called like a compactness. This is a compactness property, and what that basically means is that if something, and this is all very vague stuff, so bear with me here, but if something occurs on an infinite set, it also occurs on some finite subset. So in a way, this is a compactness theorem for proof, and that's, maybe I'll even write this out. What we've actually shown is that if sigma is inconsistent, there is a finite subset, sigma prime of sigma, that is inconsistent. So this is a pattern we'll see a lot. We'll show that we'll repeatedly be showing that a property that we'll show a various set of properties that if they hold on infinite collections must also hold on a finite subcollection, right? Or if something occurs on an infinite set, it must also occur on a finite subset, right? And this is our first example of it. We'll get to something next time called the compactness theorem, which is basically just this statement I wrote in red for model theory, for models instead of the more syntactic proofs, right? Okay. So with that all out of the way, I'm just saying what we did was actually pretty big. So let's not forget that. We return to the proof. Okay. So now we're actually done. We can just end off this. So we have shown sigma is consistent. So we've shown sigma is consistent. So every chain is upper bounded. By Zorn's lemma, we conclude a maximal element gamma exists. And that's actually the end of the proof. Okay. So we're pretty much out of time now. But there is one more thing that I want to talk about. And this pink, the part I wrote in pink in the middle, is really the meat of the proof. It's the compactness of consistency, right? If we know that, then it's really obvious. The rest of it is just, it's this interesting proof in the middle that's sort of framed inside of a Zorn's lemma proof. I want to. You can stop here. The rest of this doesn't really matter, but I do want to make some statements on did we need Zorn's lemma? Okay, so let's actually pause for a moment and have a question of cardinality. So if sigma or so if remember this is a long time ago. So now if script S is just the set P and Q, so I only allow myself 2 sentence variables. How many sentences are there? So obviously this is a think about this for a moment, but this is a think about this for a moment, but obviously there's infinitely many sentences, right? But what infinity? What infinity? Okay, yeah, think about that. See you in a moment. Okay, so importantly, there's countably many sentences. If S is only if there's only finitely many sentence symbols I ever use, there's only countably many sentences. And that's because this is the same reason that there's countably many words in the English language, right? It's like any string of sentences, right? The whole point of proving something's countable is this. I'm going to be very loose with this, so if you don't understand this, it doesn't really matter. But the whole point of proving something's countable, the whole way you do it is just you show a bijection with the natural numbers. So that's equivalent to just putting things in a list. So I could take all of the sentences ever, and I could arbitrarily say, okay, I could arbitrarily put an order on S and then the symbols and not open parenthesis, close parenthesis. I could just take all the sentences, assign some arbitrary order on these symbols, and just sort them in dictionary order, right? And it's called lexicographic order, but it's dictionary order, right? I could just basically alphabetize all the sentences, and then that's clearly a bijection. It's a list of every sentence, so it's clearly a bijection to the natural numbers. There's only countably many sentences. In this situation, the answer to this question is no. If there's only countably many sentences, we don't need Zorn's lemma at all. In fact, induction will prove this. And that's why this proof is the proof I gave is maybe not theoretically the best one, simply because it relies on Zorn's lemma when in many cases you don't need Zorn's lemma. You just need induction. But if and I'll just write this quickly, but if the size of this is uncountable, so this is where I have a bizarrely large amount of different variables, right? I can have up to uncountably many variables. So if I have uncountably many variables, I absolutely need to use Zorn's lemma to prove this. Okay, so the point is, in many cases, we can get away without using, and this is important to think about because I said last time, Zorn's lemma is practically an axiom. So there's things we may prove. There's things we may prove assuming Zorn's lemma, but it's also important to understand what's true without Zorn's lemma. So if we aren't allowing ourselves to use Zorn's lemma or any equivalent statement, I can still, as long as the set of sentence symbols is countable, I can still get away, I can still prove this statement. And it's a very simple induction on, I order all of the sentences, and then I check one at a time. It's a constructive way of getting the maximum. I basically just build the biggest chain I possibly can by taking all of the sentences and then grabbing only the ones that are consistent. All right. So, now if S is, if size of S is uncountable. Of course, I can prove this with Zorn's lemma, and I still can actually apply induction. This doesn't matter. This might not make sense yet. But in order to induct on a uncountable set, I have to assume the axiom of choice. So in order to just order an uncountable set in a meaningful way, I need something equivalent to Zorn's lemma anyway. So, okay, I'll stop there. Yeah, this last 5 minutes is definitely not important, but I just wanted to get this out of the way of whenever you prove something with Zorn's lemma, it's very important to see exactly why it was necessary, and it's just the size of the sentence symbol. So if you are philosophically opposed to the axiom of choice, you can still keep watching for a while longer, because as long as you don't have uncountably many variables, we didn't even need the axiom of choice to do any of this. Okay, so that's the end of my proof of Lindenbaum's theorem. Next time, we will use this fact to prove the final iteration will prove the completeness theorem. And with that, we will be done with propositional logic. So I'll see you next time for the last video on propositional logic. Thanks for watching.